Hi, this is a special lecture on one of my favorite topics, graph neural networks. Particularly within graph neural networks, today we'll be looking at something called graph convolutional network. So we'll be learning what is this convolution operation that we can do within graph networks. My name is Dr. Sridhar Panat. I'm a PhD from MIT, and this lecture is part of the graph neural network course. And I welcome you all. I'll be showing you how to implement graph convolutional network or GCN using a very interesting and very simple numerical example. So let's get into the lecture. Before going into the numerical example from the lecture, let us briefly see what exactly is this convolution operation in the context of graph neural networks. In a regular image where there are pixels arranged next to each other, we can consider that each pixel is a node in the graph. And we can also imagine that each pixels are connected to its neighboring pixels through imaginary edges. These nodes and edges are also part of the regular graph neural networks. In the case of images, if we are applying a convolution operation, what are we doing? We are applying a convolution mask. The mask will have certain parameters or numbers, and it kind of aggregates the values of the pixels from those that fall within the mask, right? So this is the convolution operation within images. Now, if you consider that this image is a graph network where the nodes are arranged like a grid and these nodes are connected to its neighboring nodes through edges, this is basically a graph in a Euclidean space. In the context of a regular normal graph neural network where we are not necessarily representing images, but rather maybe social media users and their interactions, or it could be cities connected by roads, basically like a map. So there will be nodes and edges. It will not be arranged in grid like this, but rather it will be arranged in a non-uniform fashion. And it can have, the orientation will not be in a plane. And essentially you can consider it to be as if the nodes and edges are present in a non-Euclidean space. So you won't be able to do normal operations that you can do in the Euclidean space. However, here also in this non-grid format of the nodes and edges, which are found in almost all of the graph neural networks, you can perform convolution operation where we can aggregate the features of all the neighboring nodes of a particular node. And this operation itself is called as the convolution operation. In the case of images, what are the features? The features are the pixel values themselves. Okay. I just wanted to mention this to give you an idea that convolution as an operation also has an analog present in the graph neural network, which is very similar to that of what we do in an image. Now let us look at a numerical example to understand how graph convolution operation is performed so that, let's say, we can perform a node classification task. Let us try to understand this with a very simple example. We will consider a graph neural network with just 3 nodes and 3 edges. What are these nodes? These nodes represent research papers. So we have 3 research papers, paper A, paper B, and paper C. Now, what are these edges? These edges represent citations. So the paper A is citing paper B is citing paper C, and paper A is citing paper C as well. So A is citing B and C, B is citing C, C is not citing A or B. That's what these arrows indicate, which paper is citing which. Now, in the graph convolution operation, what we essentially do is these nodes will have some features. Features could be number of citations each papers have, or the domain of each of these papers, like machine learning, deep learning, healthcare, agriculture, whatever. And there could be a bunch of other features for each of these papers. So those nodes will update its feature values by considering the interaction of these nodes with its neighboring nodes. And this whole process is what happened in the convolution operation in the graph convolutional network. If you don't understand what that exactly means, don't worry. It's very simple because this example is as simple as it can be. Now, let us look at these features. So firstly, let us lay some rules for these papers so that we can define the feature matrix. So we can say that paper A is broadly in the domain of machine learning. Paper B is in the domain of deep learning, and paper C has elements of both ML and DL. Now the goal is to classify each of these papers, paper A, B, and C, into one of the categories, either ML or DL. We don't want to say it has both ML and DL, which is sometimes not useful. So we want to perform a binary classification essentially. So at the end of the convolution operation, we want to be able to say that paper A belongs to ML or DL. Same for B and C. We want to be able to say whether it's ML paper or DL paper. So to make this binary classification, we will not just be considering the features of those individual papers. We will also be considering the features of the papers that particular paper cites. Now, let us come into two concepts. First is adjacency matrix, and second is feature vector. Adjacency matrix is a terminology that is present in graph neural networks. It's extremely simple. Basically, it is the weight of the edges between two nodes. So here, it's a 3x3 matrix. In this particular case, the adjacency matrix A is a 3x3 matrix because there are 3 nodes. Now, node A can be connected to itself. It can be connected to node B. It can be connected to node C. And the weight of those connections or weight of those edges are denoted by WAA, WAB, and WAC. Similarly, WBA, BB, and BC shows the weight of the edges between connections from node B to A, from node B to itself, and from node B to node C. And same for C. Now, we will assume that if a citation is present from paper A to paper B, that value, meaning that edge, is 1. If there is no citation present, it will be 0. Now, initially, paper A cannot cite itself, right? So there is no edge from node A to itself. There is no self node. So WAA is 0. Same thing applies for WBB, which is this guy, and WCC. So all these diagonal elements are 0. Now let us look at these two terms, WBA and WAB. So paper A is citing paper B, but paper B is not citing paper A. It makes sense, right? Because let's say if I am writing and trying to publish a paper, I will be citing already published papers. So when that paper was being published, my paper was not in existence, which means that paper cannot cite my paper. Only I can cite that paper. So citation cannot go both ways. Paper A cannot cite paper B, and at the same time paper A and B cannot cite each other. Only one thing can happen. So in this case, A is citing B, but B is not citing A, which means WBA is 0. WBA is this guy, right? This guy is 0, but WAB is not 0 because there is connection from A to B. Similarly, C is not citing itself, and C is not citing A or B, which means WCA, WCB, WCC, all of them are zeros, as you can see here in the adjacency matrix elements. Now let us look at WAC. C is not citing A, but A is citing C, which means WAC is non-zero. It is 1. So this is how you can understand the adjacency matrix. It's extremely simple, nothing complex. Now let's come to feature vectors. Feature vector is nothing but each of these nodes will have a vector which we can denote by VA, VB, and VC. There are different notations for these feature vectors. I just chose the notation V for the convenience. If you read papers, there will be other notations. So don't just get confused. Just focus on the concept. Now, what are the features? The features are two-dimensional, meaning in the feature vector, there are 2 dimensions. First dimension denotes whether the paper talks about ML. Second dimension denotes whether the paper primarily talks about deep learning. So ML or DL. Now here we mentioned that paper A is primarily about ML, not about DL, which means the feature vector for A, which is node A, will be 1, 0. It's primarily about ML, not about DL. So VA over here will be 1, 0. Paper B is more about deep learning rather than about machine learning. So this will be 0, 1. And paper C has both ML and DL. And this is something that we defined. You can define whatever you want. Based on that, the feature matrix, feature vector will change. So VC will be 1, 1. So these are the feature vectors, VA, VB, and VC. Now, what is the feature matrix? We denote this matrix by X. And feature matrix X is nothing but it's a collection of these three vectors, VA, VB, and VC. And it will be something of dimension 3 by 2 because we have 3 nodes. And for each node, we have 2 dimensions. For the feature vector of each node, it has 2 dimensions. It has the dimension of whether ML is present or DL is present. So that is why it's 3 by 2. All right. Now let's move on to the operations that are present within graph convolutional network. So now we will look at 5 operations. All of these operations are extremely simple. Of course, there are complex versions of these operations if the graph itself is complex. But since the graph that we are considering is exceptionally simple, I don't see any issue for you, issue with respect to understanding these convolution operations. So firstly, we do something called as self-looping. So adjacency matrix with self-loop. I will show you what this means. So what we do here mathematically is we add an identity matrix to the adjacency matrix. To get this matrix A, I think this symbol is called tilde, right? So A tilde. So the original adjacency matrix was this. We calculated it above here based on the connections going from different nodes. So this is the adjacency matrix A. So that is this. I is the identity matrix. So it is just all diagonal elements being 1. And this equal to this guy. So this is A tilde. And this is adjacency matrix with self loop. We can denote it pictorially like this. So node A being connected by with itself. That's what these 3 terms mean, right? So if you remember WAA, WBB, and CC, which we discussed over here, AA, BB, and CC, this is the weight of the edge that is going from A to itself, B to itself, and C to itself. And interestingly, we also mentioned that since a paper cannot cite itself, there won't be any self loop. So these self loop, like the loop or the connection that is going from the node A to itself, B to itself, and C to itself, does not have any physical meaning in this particular context, in this example of paper citations, because obviously a paper cannot cite itself. But the reason why this is done is because in the future step, we will be doing something called feature aggregation, where we aggregate the values of the features into a node from its neighboring nodes. And when we do this feature aggregation, if we have all of these diagonal elements to be 0, meaning if this, instead of this being 1, 1, 1, if this was 0, 0, 0, the features of its own will be neglected by that node. It will only be considering the features of its neighbors, ignoring its own features. That is not good, right? Because if paper A is about machine learning, that idea or that fact has to be taken into account. We should not be just looking at the features of the papers that this paper is citing. So because that paper may be about healthcare or agriculture, who knows? So of course we can consider the features, meaning the topic of the papers that paper A is citing, but we have to obviously consider its own features, the features of paper A itself, which is why we are doing this self-looping. I hope this step is clear to you. Now comes the second step. In the second step, we define something called as degree matrix. Degree matrix is very simple. So this A tilde is the modified adjacency matrix with self loop, right? So this was not the original adjacency matrix. This is the original adjacency matrix plus I added to it. Degree matrix D is nothing but the number of connections that are going from each node. And here we will be counting the self loop node also. Sorry, self loop edge also. So how many connections are going from A? There is one connection going from A to A. So this is the first connection. There is one connection going from A to B, second one, and one connection from A to C, third one. So the degree matrix will be a diagonal matrix because we are only denoting the connections going from A, connections going from B, and connections going from C. So this is corresponding to connections going from A, this is going from B, and this is going from C. So C is not citing any papers. So C has no edges going from from C to outward, but it has one self loop or self connecting edge, which is this. So only that is counted in the degree matrix calculation. So degree matrix being 3, 2, 1 means for node A, there are 3 connections going. For node B, there are 2 connections, and node C, there is 1 connection. You can also get this from the adjacency matrix. So basically, if you add up this row, the first row, the sum of the first row is 3. So that you can note as the degree, the first element of the diagonal. The sum of this row in the adjacency matrix is 2, and sum of this row of this adjacency matrix is 1. And you can see that they are the diagonal elements. So this degree matrix is very important because if we don't have degree matrix, imagine that we had 100 nodes, 100 papers that we are looking at. Maybe one paper is cited by 1,000 other papers. Some famous papers have huge number of citations, meaning if we have 1,000 papers or 1,000 nodes, that particular node may have 999 edges coming towards it from the other nodes. Now, if we do feature aggregation, as you will see in the next step, what may happen is that if we don't account for the fact that this node has, if a node is connected to many other nodes, if we don't account for the factor that this node has so many edges going from it, then we may blow up its feature because all the features will get added. So we have to perform some kind of normalization to account for the fact that this node is connected with too many other nodes, right? So this normalization we will do so that the feature values are not blowing up, because we are aggregating the features from all other nodes, and then we are normalizing it by the number of edges that is coming and connecting with this node, or going away from this node rather. So this degree matrix will help you for that, because now the degree matrix is telling us a story. It is saying that the node A has 3x more edges going away from it than node C. And this is a good information. We should use this information to normalize the features for node A and node C respectively. Now let us go to the next step, which is the third step. And this will be, as I mentioned, normalizing the adjacency matrix. So we have to normalize the adjacency matrix based on the degree matrix, because the degree matrix tells us how many connections are going away from that node. Otherwise, as I mentioned, we will be aggregating the features from all the neighbors, and basically the nodes with maximum number of neighbors will blow up its own features. Those features will increase when feature aggregation is done. So the normalization formula mathematically is as follows. It's A cap. So A cap equal to D raised to minus 1 by 2 times A tilde. So what was this A tilde? If you remember, A tilde was nothing but this was A plus I. We did the self looping. So this was that. And what was D? D is nothing but degree matrix. So this is the formula for calculating the normalized adjacency matrix. Now you might be wondering, how do you do this D raised to 1 by 2? It's a matrix. What is the what do you mean by raised to minus 1 by 2? It simply means you perform element wise raised to minus 1 by 2 only for diagonal elements. So it will be 3 raised to minus 1 by 2, 2 raised to minus 1 by 2, and 1 raised to minus 1 by 2. We will not be performing it on non-diagonal elements because it's not needed, and more importantly, non-diagonal elements are 0. So if you perform this, it will be 1 by 0 raised to minus 1 by 2. It is not defined. So we perform this this operation of normalization using the diagonal elements of the D matrix. So D raised to minus 1 by 2 will look like 1 by square root of 3, 1 by square root of 2, and 1 by square root of 1, which is 1 itself. So this is d raised to minus 1 by 2. Now we can calculate the normalized adjacency matrix A cap using this formula. And now we can substitute the values, right? Because now we know d raised to minus 1 by 2. So this and this is the same. And this is the self-looping adjacency matrix. So adjacency matrix added with I. We can calculate this by first multiply this with this. So multiply these two guys, and whatever product we get, multiply that with this. So that is what I did here, and you get a resultant normalized adjacency matrix that looks like this. So this is A cap, which is normalized self-looping. I'll just put it in the bracket, adjacency matrix. Now, after finishing the normalization, let's go to the next step. This is the fourth step. In this step, we do the feature aggregation, and then we transform the aggregated features. So this feature aggregation is what we have been talking so far, because to not blow up the features, we did normalization before, and now we do the aggregation itself. So the node features are aggregated by considering all the features from the neighboring nodes. So for each node, there are neighboring nodes, and those features are aggregated into that node itself. Do we have to consider this separately? Like, do we have to consider separately the fact that, oh, A is connected with B, B is connected with C, but C is not connected with A? How do we consider all of these facts? All of these are ingrained into the adjacency matrix, because we created the adjacency matrix by considering this fact in the first place. So we don't have to separately now consider which node is connected with which. It's all ingrained into the adjacency matrix. So now features are aggregated using the normalized adjacency matrix A cap. So if you remember, I'll just write here, A cap is equal to, we saw before, d raised to minus 1 by 2 times A tilde times d raised to minus 1 by 2. And what was A tilde? This was nothing but A plus I. And here A is the adjacency matrix and D is the degree matrix. Now what we have to do for performing the aggregation is something very simple. So first we calculate AX. So what is X? X is the input. Input meaning input features. So input features were the following, right? Input features, if you remember, were like this. I have a box somewhere here. Okay, I can write it here. So input features were nothing but, oh yeah, it's over here. So we had ML or DL as the feature of the paper. Paper A was more about ML, which is why this was 1 and this was 0. Paper B was more about DL, deep learning. Paper C was more about, it was about both ML and DL. And then the initial feature matrix X was 1, 0, 0, 1 and 1, 1. So this is the feature matrix, the initial feature matrix that we are talking about here. So first we do feature aggregation using this formula A prime X. So A prime X equal to, and what is A prime? A prime is the normalized self-looping adjacency matrix. X is the initial feature matrix. If we perform the matrix multiplication, this is 3 by 3, the dimension of this matrix. And this is 3 by 2. So the resultant one will be 3 by 2. So these are the resulting values of the elements of the resulting matrix. So now we did feature aggregation. So AX is the aggregated feature. Do you see what happened here? Basically, we transformed or rather we aggregated the feature matrix from initially this was the feature matrix. This was the original feature matrix. We transformed it to something that looks like this. This was 3 by 2. The resultant one is also 3 by 2. We aggregated the features into this feature matrix. Now, what we have to do is we have to transform this aggregated feature matrix using a transformation matrix W. So this is, you might be wondering, what exactly is this W? This AX is the aggregated matrix, right? So, okay, sorry, I forgot a cap here and I put the cap at the wrong place. So let me delete this. So the cap is supposed to be here. So A cap X is the aggregated matrix. And now W is the transformation that we are applying. So don't worry about this transformation. You might be familiar with the weights in the context of neural networks. The neurons that are connected to each other have certain weights acting, and often these weights are learned in the training process. So imagine that we have a weight matrix that is learned in the training process, and for simplicity, we will assume that this weight matrix is simply like a unity. Unity, so meaning identity matrix. I meant to say identity matrix. A 2 by 2 identity matrix. So diagonal elements are 1. Now what we do is we multiply the aggregated matrix with the transformation matrix, which is the unit identity matrix, and we get this resulting matrix, which is same as the aggregated one, because if we are multiplying with identity, nothing changes. So this is Z, denoted by Z, and Z is the transformed feature matrix. If I were to write what is Z in one sentence, let me write Z. Z is, I'll write the whole thing here because it will give you an idea what all things we did so far. So Z is what? Transformed matrix. And what was this matrix? Which matrix did we transform? We transformed the aggregated matrix, right? What was this aggregated matrix? This aggregated matrix was the adjacency matrix, not adjacency matrix, normalized self-looping adjacency matrix multiplied by this thing multiplied by features, initial feature matrix. So feature matrix is X. Normalized self-looping was this, right? So self-looping was A plus I. And to normalize this, we did this operation, d raised to minus 1 by 2, d raised to minus 1 by 2. Then for aggregation, what we did is we multiplied these two. So that was over here. So A cap times X. So A cap times X was nothing but d raised to minus 1 by 2 times A plus I times d raised to minus 1 by 2. And this whole thing multiplied by X. This is a matrix multiplication. And how did we transform this? We transformed this by multiplying this with the transformation matrix. This is not multiplication symbol. This is X. Okay, please note. This is not a multiplication symbol. This is X. I'm using capital X. That's why it may cause a confusion. Now, this was called as A tilde. This whole thing was called as A cap after normalization. This was self-looping. This was normalized adjacency matrix. And X is the initial feature. Then this guy is called aggregated feature matrix. And this whole thing, can I write a very ugly circle here? I'm sorry about this messed up thing. But this whole thing is called transformed aggregated feature matrix. Okay. Very simple. There are so many terms. I just took it slowly so that you can understand. So now these were the old features. These were the feature vectors, VA, VB, and VC. This was the initial feature matrix, which was the collection of these three feature vectors. Initially, before we performed all these operations. Now, after transformation, this is the, we can say X prime is the transformed aggregated feature matrix. And based on this, we can write the individual vectors, feature vectors, as the first row will be the first feature vector, second row will be the second feature vector, and third row will be the third feature vector, VA prime, VB prime, and VC prime. So this is how we transformed the value of the features of these individual nodes by considering the value of itself and the value of its neighbors. This is how we perform the convolution operation. We are not done yet. We have 2 more steps to go. Now, in the next step, we apply, this is an optional thing, by the way, we apply an activation function. Activation function is applied in the context of neural networks for dealing with non-linearity, meaning if we did not have non-linear activation functions, the neural network will not be able to approximate non-linear trends. It will only be able to approximate trends that are in a straight line. So that is why we are applying non-linearity in this case. So activation function is denoted by the symbol sigma. So this is sigma of z rather than sigma multiplied by z. Okay, so please consider this is like f of z. So sigma of a cap x w. This is not multiplication symbol. This is x. So what was a cap x w? It was the transformed aggregated adjacency matrix, self-looping normalized adjacency matrix. Transformed aggregated feature matrix. That was AXW. So now H equal to activation function applied on top of it. Now imagine that our activation function is the softmax function. And we know what is softmax. Softmax basically converts a set of numbers into a probability distribution. So if we have three numbers, if we apply softmax on top of those three numbers now will look like a probability distribution. If you sum those up, you will get 1. All the numbers will be between 0 and 1. So here softmax is applied row wise, meaning when we apply softmax, first we look at these two numbers, this guy and this guy. And as a result of application of softmax, we will get before applying softmax, I just wrote 2 by square root of 3 in its proper form so that I can use some online softmax calculator. The formula for softmax is fairly simple. You can calculate if you have the formula using a calculator, but I was a bit lazy. I just wanted to put these numbers into an online softmax calculator. But basically, if the numbers are the same, the probability are also the same, which means probability will be 0.5 and 0.5. If number is big, probability will be higher. If number is small, probability will be lower. So here you can see that this is the softmax for the first row. This is the softmax for the second row, and this is the softmax for the third row. If you sum these two things, if you get 1, you will get 1. If you sum these two, you get 1. If you sum these two, you get 1. So this is the modified feature vector after softmax activation. So feature vector, what we did is feature vector, we aggregated first using the new adjacency matrix. This adjacency matrix was calculated using what we did is we converted the adjacency matrix initially into self-looping adjacency matrix. Then we normalized it, and we used the normalized adjacency matrix to aggregate the features. Then we transformed that aggregated feature matrix, and then we got something, and that something we applied softmax through it. And this is now what is the result, this red color matrix over here. Now is the very last step. If you have waited till this point, you should be very happy because we are almost done. So just to recap before going into the classification step, right? Initially, this was the information that what was given. We had 3 papers. Paper A was citing paper B, B was citing C, and A was also citing C. C was not citing either of these papers. And we said that paper A is about ML, B is about DL, and C is about ML and DL. And our goal was to classify each of these nodes into one of the two categories, either ML or DL. So that was our goal. Now we'll be doing that. Now we'll be doing something called node classification. So let's say class 1 is ML and class 2 is DL. So we want to classify each nodes into either class 1 or class 2. So how do we do this? Based on modified feature vector, or rather modified feature matrix. So first we have the modified feature vectors as like this, right? So this we got after softmax application. We got this X prime, which is the activated modified feature matrix. So we applied softmax, and the only reason why I'm not writing softmax here is because it's a fairly straightforward function. I did not want to extend the length of the lecture by explaining softmax, because I'm assuming that you can just believe me if you don't know what is softmax, or you can look up the internet, or just go with the flow. If you already know softmax, amazing. But anyways, this is the modified adjacency matrix, and these are the corresponding vectors. First row will be this feature vector, modified feature vector. Second row will be the second modified feature vector, which is VB prime, and third row will be the third modified vector, VC prime. Now, how do we classify this? We classify this using a classification weight matrix. We denote this classification weight matrix using WC. Basically, you can consider it to be like a transformation matrix. The values of this weight matrix also, just like how values of weight matrix in a convolutional neural network is learned, this WC is also a learned weight matrix. So now what we do is this X prime over here, this was X prime. We will transform it using the classification weight matrix to get ZC, Z classification equal to X prime times W classification. Now, what are the values of the WC and dimensions? So dimension of WC is 2 by 2. And the reason for this is we want to do 2-class classification. So for that, we should have, and how many nodes do we have? We have 3 nodes. And each node could be potentially in one of the 2 classes, right? There is class 1 and class 2, which means we want a 3 by 2 matrix as the output. Now, what is one of the input? One of the input is X prime itself. This is 3 by 2. So to get 3 by 2 as output, this 3 by 2 has to be multiplied by a 2 by 2. So this is the logic behind having WC, its dimension to be 2 by 2. Now, what is the logic of these values being minus 1.1, 1, 1 and minus 1.1? The logic is simply it's a learned function. So there is no logic that I can explain to you. Just believe me, this is like a learned function. Okay, I'm sorry about that. Now, what we do is we calculate ZC by multiplying X prime with WC. This is WC, the classification weight matrix, and we get these numbers. Now we are ready to classify. Now just let me draw a rectangle here if possible, or rather just, just focus on this blue matrix. So the first column corresponds to class 1. What is class 1? Class 1 is corresponding to ML. Second column corresponds to class 2. Class 2 means deep learning, DL. And first row corresponds to node A, second row corresponds to node B, and third row corresponds to node C. Now just look at these numbers. For node A, which number is higher? For node A, this is higher, meaning the number corresponding to class 2 is higher. So class 2, the class score for deep learning is greater than class 4 score for machine learning for node A. Similarly, for node B, the class 1 score, meaning ML score is higher. And for node C, class 2 score is higher. So what does this mean? Node A will be classified as deep learning, node B will be classified as machine learning, and node C will be classified again as deep learning. So this is the conclusion. What was node A? Node A was corresponding to paper A. We classified paper A as deep learning, paper B as machine learning, and paper C as deep learning. That is the final outcome of node classification. So this means we achieved success. So just to recap what we did in this lecture, we assumed that the papers A, B, C are denoted by nodes and the citations are denoted by edges. Based on the edges, we defined an adjacency matrix. The initial adjacency matrix had all the diagonal elements to be 0. Why? Because a paper cannot cite itself. But during the operations, we added a self loop, meaning we added an identity matrix to the initial adjacency matrix. And this made all the diagonal elements equal to 1. Although this does not have a physical meaning because a paper cannot cite itself, it is important because in feature aggregation, you cannot ignore your own feature as a node. So we first did the self-looping adjacency matrix. Then next, we calculated the degree matrix. What was degree matrix? It was nothing but how many nodes, how many edges are connected from that particular node. So the degree matrix was used for normalizing the self-looping adjacency matrix. So the formula was d raised to minus 1 by 2 times a tilde times d raised to minus 1 by 2. I showed you what d raised to minus 1 by 2 is. It is the the diagonal elements of the D matrix, which is the degree matrix, raised to minus 1 by 2. The other elements are 0, they are ignored. Then what we did is we aggregated the feature by multiplying the feature matrix with the normalized adjacency matrix. So what we did is we had A cap. So we initially started with, let me write it down so that it's easy for you. We started with A. all the diagonals were 0. Then we made it into a tilde. This was a plus I. Then this guy, we also calculated the degree matrix D. Then we calculated normalized matrix a cap, which was equal to d raised to minus 1 by 2 times a tilde times d raised to minus 1 by 2. We said that minus 1 by 2 is only applied to diagonal elements. Then what we did is we calculated z is equal to a cap times x times w. So a cap x is the aggregated feature matrix and w is a transformation weight. Then what we did is we applied a softmax function. So we got h equal to sigma of z, which is equal to sigma of a cap times x times w. Now we use this x as the final matrix for classification. So what we did is we multiplied h by, we defined that zc equal to h times wc. So this wc was the classification weight matrix. And based on this, we decided whether each node belongs to class 1 or class 2. So this is how we perform node classification using convolutional graph networks or convolutional graph neural networks. I really hope you understood the idea behind convolutional graph networks from this lecture. I have oversimplified it. I'm fully aware of that. But I just wanted to give you the mathematical implementation of this in the simplest way possible. And I hope to some extent I have succeeded in that. If something is not very clear, or if you have any thoughts, or if you have any comments, feel free to let me know. But we'll meet again in the next lecture. Until then, please take care. Thank you so much.